Okay, so let's come to basically the demonstration part of this webinar here. So I already mentioned the advanced grid support functionalities, and in the next minutes I would like to show you how we implemented them and how you can use them to do automated testing. So these functions are being included in the demonstration here. So first of all, connect, disconnect, adjust maximum active power, and also some voltage support functions, namely the adjusting of power factor and volt-var, different volt-var modes. So for this purpose, for purpose of testing, I will show you two different programs which are available, which were provided by Sunspec, and they are available for Sunspec members. The first software tool we are using here is the so-called Sunspec dashboard, which enables interactive inspection of Sunspec-enabled devices. It provides also support for and kind of interacting with Sunspec devices, and it's very good to test a first implementation of the Sunspec specifications. And I already mentioned that it's available for free for Sunspec members. You can find the link also on this slide. So on this video here, you can see a brief walkthrough through the Sunspec dashboard software, which you can see the screen, the window on the right-hand side. So when you connect to a device, you can just open the device, you select the interface type and interface address, and then the software automatically scans the device for the different Sunspec models. So you can see here basically the different tabs which represent the different Sunspec models, and these models are standardized features. So for example, inverter model, it provides the readings out of the device. Nameplate model, yeah, the name says it all, it's the nameplate ratings of the inverter. Then we have also a settings model, which enables you to basically set, for example, a power limitation or program a voltage reference, frequency reference. The status model displays the current status of the device. The controls model, so that's where we're coming into the advanced grid support functions, allows what we call the immediate control functions of active, reactive power and power factor, and then we have different characteristics such as volt-var characteristics or frequency watt characteristics. And you can see here these are the models which are currently supported by the AIT smart grid converter. So, okay. Also here on the left-hand side, you can see the Typhoon HIL control center with the different, user interface panels. This will also be used later on for the demonstration. Okay. So let's jump to the next slide. So in the next few minutes, I will present you, or I will demonstrate you some of our converter capabilities using the Sunspec tools, the Sunspec dashboard, which I just showed before, and now also the Sunspec validation platform. So the Sunspec validation platform is it's a tool which is mainly used for let's say advanced users, for firmware developers, for research, and also of course for testing laboratories. It provides a framework for testing, for automated testing and validation of Sunspec compliant devices, and the full test procedures for conformance testing. This is a more complex tool. It's very powerful. You can implement almost any kind of test procedure you like, so you're not limited to run basically only Sunspec compatibility tests. You can also adapt the test scripts, for example, to meet the requirements of your local grid code. So this software is also available for Sunspec Alliance members on an annual license fee. Okay. So in the next, now we move to the demonstration. So I would like to demonstrate to you first of all some immediate control functions which are defined in the Sunspec immediate controls model, and also namely the connect disconnect, adjust maximum generation level, or this is also can be considered as a power limitation, then adjusting the power factor, and also a fixed setting of reactive power. So first of all, to the connect disconnect functionality, so I would like to show this by using the Sunspec dashboard, so not the automated tests in the test script of the Sunspec validation platform, so more the interactive control. So let's see here. So here again on the right hand side you can see the parameters of the control model, and now we are going to change the connect parameter to 0, and here on the left hand side you can see the active power output of the inverter has gone down to 0. The inverter disconnected basically from the grid. You also can see the time diagram of the active power output here. And by setting connect to 1 again, the inverter now restarts and ramps up its power to the nominal power. So also here on this slide, or in this video, you can see grid voltage readings, then power factor readings, power factor, the PQ diagram, so active versus reactive power, and also some grid settings and PV settings on the lower end. So this was a rather simple functionality which was demonstrated here, and in the next steps we would like to move on to more complex functions. So starting with the adjusting of the maximum active power of the inverter. This is also a part of the immediate controls model in Sunspec, and the parameters are first of all a set point of maximum active power output. So this set point is a % set point related to the maximum active power output of the system, or the rated power output, and also there are some optional timing settings, so that for example the adjustment of the power is not happening immediately, but you can implement, for example, ramp rates, you can implement delayed time settings, revert time settings, etc. So this is more complex, so I'm not going to show this here in this webinar because this would take too much time. So let's jump into the demonstration. So we start basically with the inverter running already in the basically curtailed mode, in a limited mode. And the limitation was first at 25%, then now it's 75%. And at the end of the automated test script, the inverter, the active power limitation will be disabled again. So you can also see here on the active power trace graph here how the power was ramped up to the inverter nominal power again. So also this is a very simple example for an automated test procedure, and also on the right hand side you can see basically the log screen of the Sunspec validation platform, and you can see the Sunspec validation platform not only basically sets or sends commands to the inverter, it also reads back measurements from the inverter, and then it compares basically the commands and the parameters with the readbacks to determine whether the inverter actually provided the correct response or not. So this was a demonstration of the active power control, and in the next test I would like to move to reactive power control, first to the control of the power factor. Also here the set point of the power factor and timing settings are the parameters which can be sent to the device. Okay, so here you can see we start with the device running at a power factor of 1 with full active power. And in the next test steps, in the next individual tests, we're going to set the power factor first to a value of 0.95 inductive. You can also see the inverter is now consuming reactive power from the grid. Now we set the power factor down to 0.9 inductive. And you can also see this here on the voltage, that the inverter actually pulls down the voltage of the grid. And now 0.8. And now we are going to ramp from inductive power factor to capacitive power factor. You can see the inverter is pushing up the voltage right now, and also run now from a power factor of 0.8 to 0.9, 0.95, and then back to a power factor of 1. And also, for example, this test can be used to automatically screen the PQ diagram of the inverter, which is a standard test in most of the certification standards today. So today, in most cases, this is done manually, but with this setup, you can implement a fully automated test. And again, here you can see, for example, here on the end of the log file of the Sunspec validation platform, the inverter power setting and the measurement of the power factor, and then see that whether the inverter has passed or failed the test. Okay, so now moving from power factor to direct reactive power control. This is also a part of the immediate controls model in the Sunspec specification. And here the set point for the reactive power can be defined in the % of a certain reference, and the reference can either be the maximum active power rating, then the maximum reactive power rating, or, and that's a very interesting option, in % of the maximum available reactive power. Because most of the inverters cannot run full active and reactive power at the same time, because they are limited in terms of maximum output current or maximum apparent power. So this last option here enables you to only use the available reactive power without curtailing the active power to provide the reactive power again. Okay, again here we will do a test, or I will show an automated test where the inverter is first running at the power at full active power without reactive power, and in the first step the reactive power is set to 80% of the reactive power, and you can see here that the inverter, to provide the necessary reactive power, had to curtail its active power. Now we are ramping up, or we are actually ramping down the reactive power from 80% to 50%. You can see also here the steps, and from inductive reactive power to capacitive reactive power. Also right now we are operating at 50% of the active power rating, now 75% and 80%. And at the end, we also have a special script to disable all the grid support functions, so that basically the device is reset to its original state. And also again here, the Sunspec validation platform automatically determines whether whether the response of the inverter actually met the requirements of the standard. Okay, now to the last demonstration for the grid support functionalities here. It's volt-var control, so this is I think it's pretty familiar for most of you. So it basically defines a reactive power characteristic or a reactive power curve as a function of the system voltage. And the aim of this function is to basically limit or reduce the influence of the generation of the infeed on the grid voltage. And this will be done in a way that if the grid voltage is very high, the inverter, the generator, will consume reactive power from the grid, thus bringing the voltage down. And if the voltage in the grid is very low, the inverter will try to actively increase the voltage by supplying capacitive reactive power. And typically these volt-var curves, they look like this. So you can see here, so this is an example also taken from a test protocol standard. And typically the curves consist of a certain deadband. So the deadband is basically an area where the inverter operates without reactive power, and only if the voltage increases or exceeds the deadband or is below the deadband, the inverter will run in the volt-var control mode. So this is a typical example. And to test the response of the inverter, we use also different voltage test profiles. So these are the test profiles which then are being used in the test. So on this slide here, you can see again the user interface panel from the HIL control center, from the Typhoon HIL control center, showing active, reactive power, and also the grid voltage at the inverter terminals. And here on the lower left-hand side, you can see the grid voltage and also the reactive power. So this graph here, this volt-var diagram as we call it, will then display the actual response of the inverter and show. And then we can see whether the response of the inverter actually met the specifications. So again, let's start the test here. So again, the Sunspec validation platform automatically sets the parameters of the inverter via the Sunspec communication interface. And you can see right now the inverter is running at nominal active power. No reactive power because the voltage is still with 1.01 per unit is still within the deadband. And in a few seconds the voltage will automatically be ramped up to see whether the inverter, how the inverter responds to an increasing grid voltage. So you can see now here at this graph that the voltage is actually going up, and at 104% of the nominal grid voltage, the inverter starts to produce or to consume reactive power, inductive reactive power from the grid. And the maximum reactive power in this case is limited to 50% of the maximum active power. So this is the setting of the curve. And we can clearly see here on this diagram the actual response of the inverter. So now, according to the test procedure, the voltage is being maintained at the maximum level for a few seconds. And now you can see also, see here on the lower right-hand side, the voltage which is now being ramped down to test also the response of the volt-var control at voltages below the nominal voltage. So you can see voltage is now already below the nominal voltage, and here in the volt-var diagram you can see the response of the controller. Okay, so now we have reached about 94% of the nominal voltage, and you can see that this is also the point where the inverter already runs at the maximum capacitive reactive power. So, and again, a few seconds hold time, and then we ramp back the voltage again. The main purpose of this of these ramps is basically to determine whether the control responds to decreasing and increasing voltages in the same way, or whether the control exhibits any kind of hysteresis or kind of delays or other things you wouldn't like to see. So that's the reason why we have these hold times, why we have these defined ramps. And for a more dynamic test, while the first ramps were pretty slow, we also have faster ramps which are going to be shown now. So basically now the voltage is being ramped up faster and also ramped down then a little bit quicker as before. And this test profile, for example, is a standard test profile which has been taken from the Sandia test protocol standard, which was developed mainly to test the grid support features which are required in the latest California Rule 21 grid code. Okay, so I think we can stop this video right now, and I would like to show you also now an example of a test procedure which we use to determine the transient response. So the first test was mainly related to determine the accuracy, the slow response of the controller, and now in this example what we do is we do a very fast voltage change, and to see whether the inverter response or how to see the transient response of the converter. So let's start the test profile again for the transient. You can have a look at the voltage here. So voltage is still at nominal, and now in a few seconds the voltage will suddenly be increased by I think about 10%. To see, to 10%, so that's 230 volt plus 10% to determine the transient response. And you can also see here that the inverter responded without any kind of time delay and in a very accurate way, which can be seen here on the reactive power time series trace graph. And now we basically step the voltage from plus 10% to minus 10% on the grid end. Because of the reactive power in feed of the inverter will increase the voltage, of course. So here these voltages at the lower end are the voltages basically at the grid, and these voltages are measured at the inverter terminal. And again, now we step back the voltage to the nominal value. Okay, and with the help of this test example, we can see how the inverter responds in a transient way to a fast change of the grid voltage. And this is also another example of a test which is being performed in modern grid codes. And for example, if you want to do these tests in a real laboratory, you would first of all need a full-scale grid simulator which allows you to change the voltage. You need to make sure that the impedances of the network meet the requirements and so on. So it's pretty challenging, and with the HIL solution, with the smart grid converter controller from AIT, you can basically run these tests on your desktop, and also you can change grid characteristics, you can change grid impedances, and you can also implement more complex control characteristics very, very easily. So, okay, let's jump to the next slide. So now let's move on to the summary of the presentation here. So what are the main applications for the smart grid converter controller and the HIL platform? So I distinguish, or I separated here the applications for different stakeholders. So first of all, for the utilities and system integrators, the concept, the platform is very useful to perform grid integration studies with advanced grid support functions, because you can take the real inverter controller and put it on into the real-time simulation and do grid integration studies with the real grid parameters and the real control characteristics. So this is much more or much closer to reality than, for example, doing pure offline simulations with grid simulation platforms. Also, you can use this for microgrid and power system studies and research. You can also, at the moment, I showed only one inverter in the system, but you can easily use this concept, this platform, also to run, for example, multiple converters in a simulated environment and investigate, for example, the interactions of different control functionalities. For equipment manufacturers, it can be very useful to add Sunspec protocol support to existing products. So we also offer this Sunspec server, which is basically a separate block in our concept as a kind of add-on support for existing projects. Also, manufacturers may use the AIT Smart Grid Converter as a reference design for new products, or use the complete system to support their development of plant controllers, energy management systems, and so on. Last but not least, also for the research world, it can be very useful as a generic converter model for DER integration research. It's a reference design of a Sunspec compliant grid converter, which can be used, for example, to validate power system control strategies, and also to develop test procedures. So the last point, for example, the last application, that's where the AIT Smart Grid Converter is already being used by Sandia National Laboratories in the United States to support their development of automated test procedures and test scripts to validate the compliance of inverters. So how does it address your application needs? For industrial and academic R&D, design, validation, and test procedures, it can act as an all-in-one solution for R&D applications. You can use AIT Smart Grid Converter HIL Connect to perform R&D on Sunspec communication concepts. And what you just need, the only thing you need is the equipment, the HIL Connect, a Typhoon HIL box, and a license for the Smart Grid Converter. Also, I already mentioned for manufacturers, an option is to add Sunspec compliance to existing products by using AIT Sunspec server package. And also during product development and testing, the AIT Smart Grid Converter can be used as reference design to support development, test, and validation of control and communication equipment. So that's the end of my presentation today. So before I close, I would like to acknowledge some support and some people, and also say a special thank you to, of course, people at Typhoon HIL for supporting our development and design, then to Jay Johnson at Sandia National Labs, then people at Sunspec Alliance, and last but not least also the Austrian Ministry for Innovation for funding some of our activities in the international collaboration and the development of the Smart Grids Converter. So that's the end of my presentation. I would like to thank you for your interest, and I'm looking forward to hear your questions. So thank you.